Assalamualaikum. Welcome back to Sir K Lab's Physics and Chemistry tutorial for high school students. Moving from state to state, that's exactly our topic in today's episode. So join me in exploring problems involving phase changes of substances. Just stick around, watch and learn. Question number 1. You cool a 100.0 gram slug of red hot iron whose initial temperature is 745 degrees Celsius by dropping it into an insulated cup of negligible mass containing 85.0 grams of water at an initial temperature 25.0 degrees Celsius, assuming no heat exchange with the surroundings. Question letter A. What is the final temperature of the water? And letter B. What is the final mass of the iron and the remaining liquid water? Use the constant specific heat of iron equal to 0.451 joules per gram Celsius degree. Specific heat of water or liquid water equals 4.184 joules per gram Celsius degree, and the heat of vaporization of water at 100 degrees Celsius equal to 2,260 joules per gram. We let Q1 be the amount of thermal energy liberated by the piece of iron as it cools down from 745 degrees Celsius to 100 degrees Celsius. And we apply the formula Q sub 1 is equal to mi Ci delta T, right? This means that uh, the heat that will be liberated by the piece of iron can be determined just by multiplying its mass by its specific heat and its change in temperature delta T. That is 100.0 grams times 0.451 joules per gram Celsius degree times 645 Celsius degree, which is the difference between 745 degrees Celsius and 100 degrees Celsius. And doing our math, we get Q1 equal to 29,090 joules. We also let Q2 be the amount of thermal energy the water has to absorb to reach its boiling point of 100 degrees Celsius. And Q2 is also determined using the same formula, Q equals mc delta T. That is 85.0 grams times 4.184 joules per gram Celsius degree multiplied by the delta T of water, which is 100 degrees Celsius minus 25 degrees Celsius, which is 75 Celsius degree. Hence, The value of Q2 equals 26,673 joules. Notice that there is a difference between Q1 and Q2. So we label that difference as Q3. That is 29,090 joules minus 26,673 joules, or Q3 equals 2,417 joules. All right? So this is the amount of thermal energy that is left, all right, as a result of the liquid water absorbing 26,673 joules, all right, in order for the liquid water to reach 100 degrees Celsius, all right. So this value of Q2 is in fact uh, the thermal energy that is liberated by the slug of iron, all right. But it only utilized 26,673 joules. So there is still uh, an available amount of thermal energy left, 2,417 joules. All right. So what happens to this extra amount of thermal energy? The fact that iron and boiling water, all right, are already in thermal contact. So what happens is that the boiling water will still continuously absorb further amount of thermal energy from uh, the slug of iron, right? In other words, because of this available 2,470 joules, okay, a certain amount of the mass of the boiling water will actually be converted into steam at 100 degrees Celsius. All right? So, we are interested in determining the mass of the boiling water that will turn into steam. And we denote that by M sub W. All right? So, in determining this mass of the boiling water that will turn into steam, we simply divide the amount of thermal energy Q3 by a constant known as the latent heat of vaporization of water at 100 degrees Celsius. That is 2,417 joules divided by 2,260 joules per gram. So this is the value of the heat of or latent heat of vaporization of water at 100 degrees Celsius. Right? So dividing these two quantities, we will get the mass m sub W equal to 1.07 grams. In other words, 1.07 grams of uh, boiling water will in fact be converted into steam. Okay, a steam that has a temperature of 100 degrees Celsius. All right, and answering the given question, how much or what is the mass of the boiling water that remains, okay, after the two substances has reached the thermal equilibrium temperature, which apparently is 100 degrees Celsius. All right. So to get this mass of uh, boiling water, we simply get the difference of the original mass of water, which is 85.0 grams, minus the amount of boiling water that has turned into steam, 1.07 grams. So that gives us 83.9 grams of boiling water remaining. And likewise, we are also asked, what is the mass of the iron? All right, at this thermal equilibrium temperature of 100 degrees Celsius. All right, our answer, of course, is that the mass of iron remains 100.0 grams because during this whole process, iron does not undergo any phase change. All right. Uh, when the slug of iron uh, liberated this amount of thermal energy, all right, what happened was that uh, its temperature just dropped to 100 degrees Celsius, but no change in phase whatsoever. All right. So we don't expect the iron uh, to what we call uh, solidify because initially it's already in solid form. All right. Uh, just because it loses that amount of thermal energy, all right, doesn't mean that the state of iron will somehow change. Not really. All right. So that means the amount of iron will still remain intact, equal to 100.0 grams. Our last question, number 2. As a physicist, you put heat into a 500.0 gram solid sample at a rate of 10.0 kilojoules per minute while recording its temperature as a function of time. You plot your data as shown in the figure. And question letter A, what is the latent heat of fusion for this solid? And question letter B, what are the specific heats of the liquid and solid states of this material? As shown in this temperature versus time graph, we base our answer to question number 2A, which is asking for the latent heat of fusion L sub F of the substance. All right. So in answering that question, we will base it on this particular graph line, the horizontal graph line that is being highlighted now. All right. And that corresponds to a time of uh, an elapsed time of 1.5 minutes from t equals 1 minute to 2.5 minutes. Okay, this corresponds to a thermal energy being absorbed by the substance without changing its temperature. All right, notice that the temperature remains 10 degrees Celsius during this time interval. All right, so even if the substance is continuously absorbing thermal energy, okay, its temperature remains the same, no increase in its temperature. All right, that's why the term latent fusion is associated to that process whereby a substance, even if it's absorbing thermal energy, seemingly its temperature doesn't rise. All right, latent means hidden. All right, so it looks like the uh, the amount of thermal energy or heat that the substance absorbed is apparently being uh, or is hidden, hence the word latent heat of fusion. All right. So during this time interval, the thermal energy absorbed by the substance in 1.5 minutes is equivalent to 15.0 kilojoules. All right. Or that is 15,000 joules. So if we divide that by the mass of the substance, 500.0 grams, we will be getting the computed value of the heat of fusion of the substance. That is, L sub F equals 30.0 joules per gram in three significant figures. All right? So, again, we emphasize that apparently 10 degrees Celsius is the melting point of this substance. And moving on to question letter B, the first question is asking for the specific heat of the substance when it is still in its solid state. All right. So at time zero, notice that the temperature of the substance or its initial temperature is understood to be negative 5 degrees Celsius. All right. So when it's heated constantly for 1 minute until its temperature rises to 10 degrees Celsius, all right, the straight diagonal graph line suggests that it is absorbing, all right, an amount of energy corresponding to 10.0 kilojoules, all right, until the temperature reaches 10 degrees Celsius, which we said earlier is apparently the melting point of the substance. All right? So the formula for determining the specific heat of the substance is just the usual formula. We just divide the amount of thermal energy that is absorbed, that's capital Q, by the product of the mass of the substance and the change in temperature delta T. That is 10.0 kilojoules, that's actually 10,000 joules, divide that by the product of its mass, 500.0 grams, and the time interval delta T, 15.0 Celsius degree, because from negative 5, all right, the temperature rises to positive 10 degrees Celsius. So if you're going to deduct the final temperature minus the initial temperature, that's 10 degrees Celsius minus negative 5 degrees Celsius, that will give us a delta T of 15.0 Celsius degree. So, doing your math, we will get the value of the specific heat of the substance when it is in its solid state. So, C sub S equals 1.33 joules per gram Celsius degree in three significant figures as well. For question letter B, what is the specific heat of the substance at its liquid state? So we use the same formula, all right? C sub L is just equal to the amount of heat that it absorbs, big Q, divided by the product of its mass and the change in temperature, delta T, all right? This uh, process of increasing the temperature, all right, from its melting point or freezing point, which is apparently equal to 10 degrees Celsius, all right, until it rises to 40 degrees Celsius. So we are talking about this particular graph line, all right, uh, diagonally straight graph line, all right, corresponding to a time of 1.5 minutes also, all right, starting from 2.5 minutes until a time of 4 minutes, all right. So that means during this process, the amount of thermal energy that the substance absorbs in 1.5 minutes is also equal to 15.0 kilojoules or 15,000 joules. All right. So when we divide that by the product of its mass and the change in temperature, which is 30.0 Celsius degree, because from the uh, final temperature of 40 degrees Celsius, all right, minus its initial temperature of 10 degrees Celsius, that's how we got 30.0 Celsius degree, all right. So take note that during this uh, process represented by this graph line, the substance is already in its liquid state, all right. That's why what we are talking about now is the specific heat of the substance when it is in its liquid state. So, computing for this value of Cl, all right, we get a value equal to 1.00 joules per gram Celsius degree, all right. So that is the specific heat of the substance when it is in its liquid state, all right. So we are done with our tutorial. Until the next episode, mabuhay, Masya Allah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.